Hello, my name is Greta Savitsky. Welcome back to the multi-part tutorial on system dynamics modeling and STELLA software from IC Systems. Like I said, this is a multi-part tutorial. This is the third video. If you haven't seen the first two videos, I recommend going back and watching those first, where we go over some basic terminology about systems and system dynamics. And then in the second video, we talk about patterns that system dynamics models are great at picking up on, like feedbacks. In this video today, we're going to be talking about the basic components of a system dynamics model and how they work together. So because many people working with system dynamics models are not mathematicians, but are rather domain specialists looking to use system dynamics modeling more as a tool to understand their study system better. There are several different types of system dynamics modeling software available to make it more accessible to these domain specialists. There are several different brands of system dynamics modeling software. The one we're working with in this tutorial is STELLA from IC Systems. Another common one is Venism. But all system dynamic software works with the same three basic components. And those are stocks, or the representation of the storage of a system's units over time. Flows, which are the rate and direction of change in those stocks. And converters, which are neither stocks nor flows, but represent any process or constant that affects stocks and flows. So let's get a little bit deeper into these three components. Again, stocks are a memory or accumulation of the units in a system over time. Some examples of this might be population size, how many people are in a population, inventory levels, how much inventory is in a warehouse, carbon stocks, how much carbon is in the terrasphere or the atmosphere, energy storage, how much energy is stored in a battery or in the power grid, or reservoir levels, like this picture here, how much water is in a reservoir. So we're not worried so much with the flows in and out of the reservoir here. We're more concerned with how much water is actually in the reservoir. That's our stock. The change in these stocks is a flow. So that's the rate of change and the direction of change of a stock over time. Some examples could be population growth. So how quickly or slowly is our population changing? Is it increasing or decreasing? Consumption rate, how much are people buying goods? Carbon emission and sequestration, so kind of thinking about a carbon pool as a stock, for example, the atmosphere as a stock of carbon, then the flow would be how quickly are we emitting carbon into the atmosphere and how quickly is it being pulled out of the atmosphere through sequestration. Material extraction, so how quickly are we mining materials out of the Earth's surface. And finally, getting back to our reservoir example, water withdrawal. So how quickly are we draining our reservoir? The third component is a little bit trickier to explain. It is neither a stock nor a flow. It's called a converter. This is a system component that represents a process or a constant that's going to affect either rates or either flows or stocks within a system. So some examples of this could be if we're looking at infection rates of a disease, the amount that that disease is transferable, so its infectiousness, is going to determine how quickly a disease spreads and how many people are infected. Available resources might constrain population growth. So again, that's neither a stock nor a flow, but does affect both the stock and the flow in population dynamics. Or climatic factors control how quickly plants grow. So if we're looking at plant growth rate as our flow and biomass as our stock, then climatic factors are going to change how quickly that plant is growing. Let's take a simple example to understand this concept a little bit better. So through building models with these stocks and flows, we are bringing together all of the components, all the important components of a system through directional effects. And then the software converts all of these connections into differential equations that represent the system and how its parts affect one another. So a bathtub, for example, our stock is going to be the tub itself. We're interested in how much water the tub is holding. Our flows are going to be water coming out of the faucet and water draining out of the drain. And for this example, we're going to say our converter is the faucet handle. So our stock, our bathtub, is going to fill up with water as water comes out of the faucet. The direction and magnitude of our flow is going to be whether the tub is receiving water or draining water or both, and how quickly both of those processes are happening is going to affect the level of water in our stock. And our converter, the faucet handle, is going to control how quickly water is coming out of that faucet. And so once we have our model all built in our system dynamics modeling software, from there we can simulate this bathtub by using some initial conditions and then running through our differential equations for our desired time span to look at how the stock or the amount of water in our bathtub might change. We can compare the output of our model to real data. This example is not that applicable, but if we're thinking about something like population growth or disease modeling, a lot of the time there is data that we can compare our model to make sure that it's accurate, that it's an accurate representation of the system. And finally, we can experiment with our model by manipulating initial conditions or relationships within the model. So for example, I might do a run of this bathtub model starting with the bathtub totally full and seeing how that stock changes. And then I might try again with the bathtub starting at empty and see the dynamics from there. Or I might change how far the faucet handle is turned and look at how that might affect the different flows and how those changing flows might affect the stock. This has been a quick overview of the 3 components that make up a system dynamics model. Thanks so much for joining, and please join me in my next video where I will talk about causal loop diagrams and how we visualize the feedback loops in system dynamics models.